In layman's terms, as often taught to high school students, fluids can be defined as a liquid or a gas. As usual with introductory physics and chemistry concepts, this statement is more or less true, but generally works. A beaker of gas you'd imagine in a mad scientist's lab, and the orange juice someone would drink for breakfast are definitely both examples of fluids. The list of things that are fluids could go on for a very long time, so I'll spare the details on that front. While liquids and gases show a lot of the same fundamental behavior, there are distinct differences between the two. One of these differences is the material's ability to compress under pressure changes. Mathematically, a material's compressibility boils down to the material's volume rate of change with respect to pressure over its volume. But the conditions of the material have to be examined as well, and it gets complicated quickly. Really, when we're looking at compressibility, we're examining the effect of the density of material and how it changes under a load. Density is a material property which determines how massive an object is for a given volume. That's why you can take the same volume of lead and a dry sponge, weigh them, and find that the lead is much, much heavier. Since density is defined as the mass over the volume for a bulk material, the effects of compressing a given mass over a specific volume can be analyzed for liquids and gases. For two identical masses under the same increase in pressure, a gas will generally compress quite a lot while a liquid will do more or less nothing. The mass didn't go anywhere, it's just within a smaller volume now, so the density of the gas increased quite a lot while the density of the liquid increased by about zero. For the liquid, this condition is called incompressible, and it is applied in many situations as a fundamental assumption in fluids problems. While the explanation provided was with respect to an increase in load, the incompressible condition places the material's density as a constant with respect to any condition. This allows for solutions for flow regimes to be computed with relative ease. Emphasis on the relative. Still, with appropriate identifications of the problem parameters, solutions for flows, such as that in pipes, ducts, or channels, can be easily solved using this framework. Computational analysis also allows for the modeling of more complicated geometries in 3 dimensions. With some fundamental assumptions in place and appropriate boundaries, nearly anything can be modeled. The key is that the assumptions must be appropriate. How appropriate constant density is as an assumption certainly depends on what it's being applied to. A good example to demonstrate this is the effect of how temperature affects the density of water. As water heats up, or is pressurized, it expands or shrinks, and the density changes. At least when the pressure is 1 bar, in the entire range of temperatures where water is a liquid, the change in density is only about 40 kilograms per cubic meter. The question then becomes that of assessing, is that a lot? And there isn't really a clear answer. The difference between accounting for compressibility and assuming a situation as incompressible can make an enormous difference, or practically none at all. Evaluating the relevant parameters in a scenario truly make the difference in whether or not compressibility must be accounted for. It's a tough scenario to think of at first because it depends on both the actual magnitude of the difference in results and just how precise their solutions need to be. It's probably best to go over some examples at this point. There will be more of a divergence from math at this point, because otherwise this video would literally be just deciphering equations for its entire length. Mathematics is a fantastic tool, but in order to really be able to utilize it, you have to understand what's going on in a given scenario. Having the derived physical laws apply to the regime, but it still actually has to be solved. The compressibility of water is important to consider in 2 very general cases: when extreme precision is required for control purposes, and when something exciting happens within a flow regime. We'll talk about the second phenomenon in this video to show what can happen under special conditions. A good place to start with in describing these special flows is the phenomenon of cavitation. Cavitation is basically the boiling of water in response to a pressure change. It occurs when a flowing fluid drops the fluid's liquid pressure below its vapor pressure, and bubbles of gas begin to form in the liquid. In most applications, cavitation is pretty bad because it alters the mechanics of the flow regime and causes things to break down. In pumps, for example, cavitation is avoided by keeping the flow parameters at the inlet above a net positive suction head. If this requirement isn't met, the pump becomes unstable due to vibrations and a drop-off in the outflow and outlet pressure. An experimental setup was run to examine the phenomenon of cavitation. 2 scenarios were run as a fluid was allowed to pass through a pipe. The first scenario has loading of tap water at room temperature, and not much exciting can be seen in the flow regime of the pipe. The second example has heated water pumped at an increased head. It is difficult to see in the video, but there is some sloshing and bubbling at the top of the pipe. So cavitation can be destructive. We know that, but we still haven't really touched on what it is other than there are bubbles now. It's the mechanics of these bubbles which make cavitation such an undesirable process. The bubbles produced aren't stable. It's not like they just sit along on the surface and behave nicely and don't do anything. They get carried around in the flow, interacting with other bubbles in the wall, and react to pressures within the flow regime. This is yet another case of the math being very messy to deal with. When the pressures are high, these bubbles implode. This implosion is the interesting bit. When the differences of the pressures on each side of the bubble is large enough, it destabilizes and collapses inward onto itself. The gaseous bubble is compressible, and will react to the external forces squishing it inward. The imploding bubble causes a shock wave in the medium, which carries the damaging force which wears away at solids, such as in the pump example. Shock waves themselves are another example of special circumstances where fluid compressibility becomes an important consideration. Shock waves represent a discontinuous change in fluid properties across a thin shock front which travels through a fluid medium. These flow conditions are governed by the Mach number of the fluid. The Mach number is a dimensionless parameter which details the speed of a fluid in motion relative to the speed of sound in the same fluid. This constant is used to classify flows based on their speeds, but also corresponds to the responsive pressure to a change in density as its root. In a normal, one-dimensional shock wave, the Mach number upstream of the flow is greater than 1, and the Mach number downstream is less than 1. The upstream side is where the elevated pressure exists. Shock waves are much more common in gases than in liquids due to the ready compressibility of gaseous materials, but loading and pressure can certainly make the phenomenon occur in water and other liquids as well. Liquids obviously fail to obey the ideal gas law, so the mathematical description of the governing equations has been omitted in this case. The keynote to acknowledge in a shock wave calculation is that the laws of thermodynamics are relevant, and the solution produced must acknowledge an entropy increased. That's just the nature of the universe. The shock wave itself exists as a pressure front and is usually very thin, on the scale of microns. To describe a shock wave, the fluid properties immediately in front of it and behind it are considered as the control volume of the flow. The shock wave travels through the fluid at a given rate, but if the reference frame is taken to be with respect to the shock wave, it can be analyzed until it reaches an external surface. With knowledge of the upstream conditions, the downstream conditions can be solved using appropriate calculations or assumptions. Of course, more complicated geometries exist for shock waves, but that once again becomes a problem which is solved by computational analysis. Computational analysis is a very powerful tool, but its real power comes from understanding and applying the behavior of fluid regimes. Understanding a regime includes understanding fluid compressibility and under what conditions it should be accounted for. So, fluid compressibility is a phenomenon which has unique applications. The incompressible assumption generally makes life easier, but certainly isn't a catch-all for every scenario. Examining compressibility really gives insight into the field of fluid mechanics. Understanding the parameters of flow which make it unique, and then using the appropriate methods and tools to solve the problem.